Welcome to the part 2 of SPA2 session. Till now, we have discussed the fine grain fitness of SPEA2 as well as we have done the diversity operator, that was kth nearest neighbor method. So, if we look into the framework, the generalized framework which we are following, so for SPA2 we have finished step from 1 to 6. In this one, we started with the initial population and we kept our archive empty. Thereafter, we assign the fitness to all the solution in the population and we copy all of them into the archive. Inside the while loop, we perform binary tournament selection operator with replacement that created a mating pool. In this mating pool, we perform crossover and mutation using SBX crossover operator and polynomial mutation to create another new population. So, this part we have finished in the last session. Now, we will see how the environmental selection or the survival stage that has been developed with SPEA2. If we look into the algorithm, step 7 suggests that we have to first combine the new population and the current archive, and then we will be assigning the fitness to the combined population. Thereafter, we will see the number of non-dominated solution, which is currently represented as capital N, and in the subscript you can say NDS. NDS stands for non-dominated solution. When we are finding the number, there are 3 cases. As we can see in step number 8, the number of non-dominated solution can be equals to the size of archive. In this particular case, we copy all the non-dominated solution into the archive. If we have number of non-dominated solution less than the size of an archive, in this particular case, we first copy the non-dominated solutions to the archive and thereafter we are going to copy some dominated solution based on the fitness till our archive is full. In case the non-dominated solutions is more than the size of archive, that is we can see in step number 13, then we have to eliminate some non-dominated solutions. This we are going to eliminate one by one by using the truncation operator till the archive size is full. In this step 15, we take an increment of 1 and we will be moving in the loop, this is the while loop, till our termination condition gets satisfied. So, let us now understand how the survival stage is developed with the SPA2. We are going to discuss the 3 cases first and then we will take our example which we were solving in the previous session. Here, first of all, as we have to combine the offspring population and the current archive, so that will become the combined population for now. Now, since we have to make the archive for the next generation, so we have to fill or we have to choose the best solutions n bar solution into the archive. So, graphically if we see that we have the population, we have the archive, we are combining it and we are looking for the solution which have fitness smaller than 1. As per our earlier discussion, we know that this condition satisfies when the solution is non-dominated. Once we have identified the non-dominated solution in the combined population, so there will be three cases as we discussed. First case is the number of non-dominated solution is equals to the size of archive. Second case is the number of non-dominated solution is smaller than the size of archive, and the third case is number of non-dominated solution is greater than the size of archive. So, let us see how we can do it. So, in case 1, when the number of non-dominated solution is the same as the archive size, then we copy all these non-dominated solution to the archive, and at this stage the survival stage of SPA2 is over. The second case is when the non-dominated solution is less than the size of archive. So, in this case, first of all, let us copy all these non-dominated solution to the archive. From this particular condition, it says that still there is a size left in the archive in which we can copy some solution. So, we are going to copy the solutions having fitness Fi greater than 0 in an ascending order of their fitness value till the archive is full. So, in this case, some dominated solution will be copied so that the archive will remain full. At this stage, the SPA2 survival stage is over. Case 3 is when the number of non-dominated solution is greater than the size of archive. In this case, we are going to calculate sigma ik. As per our earlier discussion, this sigma ik is calculated using kth nearest neighbor approach. So, once we calculated the sigma ik, we will find the solution which is having the least sigma ik value in the set of non-dominated solution. So, this particular solution will be removed, and this process we will be repeating till the size reduces to the archive size. When we are removing such solutions one by one, then rest of the solutions we are going to copy in the archive, and that finishes the survival stage of SPA2. The operator which we have discussed for case 3 is called as truncation operator, where we are removing the solution one by one. So, basically we are removing the non-dominated solution one by one based on the sigma ik. The less value of sigma ik signifies that this particular solution is more crowded. So, therefore, it should be removed. So, now we will see that in the current example which we are solving, how we can update the archive. Now, if we look into the figure here, we have combined both the population, that is the archive, and the population which we get after crossover and mutation. Here, the notation A stands for the archive member, and the notation P stands for the population which is created after crossover and mutation. So, therefore, we are representing or referring this particular population as an offspring population. Now, we know that if we want to assign a fitness to any solution in the combined population, we have to first calculate the strength of a solution. As an example, I have taken few solutions to understand how we can calculate the strength followed by the raw fitness. If we look into the figure now, in this particular figure, let us choose solution A1. In this particular solution A1, in order to calculate the strength of this solution, we have to find the number of solution it dominates. We know that since it is a minimization problem, so both the objective are minimization as well as it is a two objective problem. So, if we take A1 as our reference and if we look into the first quadrant, we can see how many solutions are dominated by A1. Looking into the figure, we can see that the solution P4 is dominated by A1. Since A1 is dominating one solution, the strength of A1 is 1. Let us take another case. In this particular case, we have chosen the solution P8. Now, if we are going to calculate the strength, we can see that if I take solution 8 and if we look into the first quadrant with respect to the solution P8, solution number A3, A2, P1, A6, A7, P6, A1, P3 and P4, these are the solutions which are dominated by P8. So, if we can see the complete list on the right hand side and if we count the number of solutions here, so the strength of P8 will become 9 because it is dominating 9 solutions. Similarly, we can calculate strength of all the solution in the combined population. So, if we see the figure on the left hand side, so the first quadrant of each solution are shown, and by looking into the first quadrant, we can find that the strength of the members in the combined population that are given in the table. Once the strengths are given or calculated, the next step is we have to find the raw fitness of each solution. As per our earlier discussion, raw fitness is the summation of the strength of those solutions which are dominating the given solution. So, we will see few examples here of the raw fitness. If we take solution A1, in this case, since it is two objective minimization problem and we take A1 as our reference, and if we look into the third quadrant with respect to solution A1, the solutions which are lying in the third quadrant, we can see that A3, P8, P2, A8, P7, similarly P3, A4, A5 and P5. So, these are the solutions which are dominating A1, meaning that once we get the list of solutions which are dominating A1, we have to take the summation of the strength of all such solutions. So, here we have written the strength of those solutions. By adding them, we get the strength of solution A1 is 60. So, we remember that if the raw fitness of any solution is a large number, meaning that it is dominated by many solutions and therefore, it is not a good solution, and the number 60 for solution A1 represents the same. Let us take the another solution to find out the raw fitness. Here we are choosing say solution P8 and looking at the figure on the left hand side, and if we take P8 and with respect to this solution, if we look into the third quadrant for the minimization problem, we can see that there is no solution which is dominating P8, meaning that the raw fitness of P8 will become 0. Moreover, we also know that if any solution is having raw fitness equals to 0, that solution will become the non-dominated solution in the current set of current set of solution or the population. If we are going to follow the same procedure for all the solution, we can calculate the raw fitness for each and every solution. So, here we can see in the figure that we have drawn the third quadrant for each and every solution, and accordingly when we are going to make a summation of the strength of those solutions, we can find the raw fitness. So, the table on the right hand side shows the solution, its strength as well as its raw fitness. Similarly, for the population, its strength and the raw fitness. It is noted that we are calculating the strength and the raw fitness of a combined population. From this particular table, we can see that the population member P2, P5 and P8, they have a raw fitness equals to 0, meaning that these solutions are going to be the non-dominated solution. So, the number of non-dominated solution in the current set is 3. Now, we are in a position to apply the survival stage of SPEA 2, because we know how many are the non-dominated solution. So, in the current set, since we have number of non-dominated solution 3, which is less than n bar, which is the size of an archive. So, the first step is, let us copy all these non-dominated solution, and thereafter we are going to copy dominated solution using the fitness. So, initially the archive for the next generation is kept empty, and thereafter we are going to copy the non-dominated solution. Once these non-dominated solutions are copied, so we know that currently the size is 8. So, we can copy another 5 dominated solution. Now, if we look at the raw fitness of the solution, so solution P2, P5 and P8 are copied. Now, we will see which solution has the least fitness. From the given table, we can see the solution 3 has the least fitness, raw fitness. So, therefore, A3 is going to be copied in the archive. So, the updated archive will include A3, as we can see on the right hand side. Now, we have a space for 4, and we have copied 4 solution. So, after copying 3, so the next best fitness we can see with solution A8 and a P7, that is 12. Now, since we have a space, so we are going to copy these 2 solutions into the archive, and now this is the current archive which has copied 3 plus 1 plus 2, basically 6 solutions. Since we have copied 6, still we have a space of a 2 solution to fill the archive completely. As of now, the solutions having the fitness, the raw fitness of a 12 are copied. So, if we look into the next best fitness, we have solution A5 having a fitness of 17, and so A5 and then followed by A4. So, since these 2 solutions can be accommodated, so we are going to add them into the archive archive, and these are the solutions which are copied into the archive for the next generation. Since the archive is already full, so we can say the survival stage of SPEA2 is over. Now, it is important to note that we do not need to calculate DI for the given set of solutions, since we can easily copy 8 solutions without any time. It means that when we are calculating the fitness of any solution, so the fitness is made of the raw fitness plus the diversity Ti. In the current scenario, we can see that even without calculating the diversity Di, we can copy the H solution without any tie. However, if any scenario comes where there is a tie and we do not know which solution we have to copy in order to fill the archive, then we have to find out this Di and then we are going to copy the solution based on the fitness. So, that finishes the survival stage of SPEA2. And if we look into the figure now, here you can see that we started with the initial archive as shown in the left hand side figure, and thereafter after one generation we can see the updated archive. On the same scale of F2 and F1, we can see that the solution after one generation, they started moving towards the Pareto optimal front, and that is what we are expecting, that generation by generation the archive will be updated and the non-dominated solution will be emphasized, and these solutions will be moving towards the Pareto front and finally converges on the front. Once the survival stage is over, we increase the counter by 1. So, we can see here that we increase the counter by 1. So, we get t is equals to t plus 1 2, and still we are in the while loop of generation. So, in the second generation again we are going to apply the same set of operators such as tournament selection operator, crossover and mutation, and then finally the survival stage we are going to apply till the termination condition get satisfied. Now, in the current example which we have taken, the population was evolved in such a way that we can see that the case 2, where the number of non-dominated solution was less than the archive size, was encountered. So, in that case we copied the non-dominated solution followed by the dominated solution in order to fill the archive. But what we expect is, when we are running SPEA2 for further generation, then we may realize that there are many non-dominated solutions in the combined population. So, at that particular stage we have to copy n bar equal to 8 solution for the given problem. So, as a representation basis, we have taken one more example in order to understand the case 3, when the number of non-dominated solution is more than the archive size. We can see from the slide here that we will be understanding the truncation operator for case 3. So, in the figure which is shown in the left hand side, here we assume that this is the combined population after few generations. So, here we have taken say all 16 solutions, as you can see in this particular figure. Now, in the current situation, as we know, we have to choose the best n bar solution, which is 8, for updating the archive. So, from the figure it can be observed that all the solutions are the non-dominated solution. So, here as a spatial representation we have shown this particular dashed line to show that all these solutions are the non-dominated solution. So, since the number of non-dominated solution currently is 16, which is greater than the n bar, so we are going to use the truncation operator, which is the case 3. In this case, we are going to use kth nearest neighbor approach, and in this method we will be calculating the sigma ik value. So, let us see how it is working. So, first of all, we have to find out the minimum and maximum in both the objective. It is only because we want to calculate the distance in the normalized objective space. So, from this figure, f1 min, f1 max are written here. Similarly, f2 min, f2 max are given here. Now, let us calculate the normalized distance between solutions 1 and 2. When we are going to calculate, this distance is coming out to be 0.147. So, the distance means we are talking about the Euclidean distance in the objective space. Similarly, I can find the distance of a solution 1 with the other solution. So, the representation such as D1 3 meaning the distance between 1 and a 3. Similarly, 1 and a 4, 1 5, etc. Now, after sorting the distance, we can find the kth element. So, sigma 1 k equals to 4. So, we remember that this kth element we find with the rule that k is equals to under root of n plus n bar. N is the population size and n bar is the archive size. So, after sorting, we get the sigma 1 k value. Similarly, if we are going to calculate sigma I k values for other solutions, so we have tabulated all these values. So, for all 16 solutions, sigma I k values are given. As per the truncation operator, we have to find which is having the minimum sigma I k value. So, from this particular table, we can see that the solution 5 has the minimum sigma I k value, and therefore, it should be removed. So, here if we look into the figure on the left hand side, this particular solution 5 should be removed from the current set. If we remove it, we can see the updated figure right now. In this figure, you can see the solution 5 is missing. Now, since the solution 5 is removed, we have to again calculate the sigma I k value for the updated population. So, it is an important point that as soon as we are deleting any solution, we have to recalculate sigma I k value for the updated population given in the figure. So, let us these are the again sorted list of the sigma I k value for the rest of the 15 solution. From this particular table, we can see the minimum value is corresponding to solution number 8, that has to be removed. So, we are going to remove the solution number 8. So, what we can expect at the last is when we will be removing these solutions one by one. So, we are going to get the diverse set of solutions here that will be updating our archive. So, here these are the diverse solutions which we can see after removing the solution one by one using the sigma I k value. Now, we will be looking at the simulations of SPEA2. So, till now we have done the hand calculation for one generation of SPEA2. We also took a case of truncation method in which we are removing the solution one by one when the number of non-dominated solution is more than the archive size. Now, we will be testing this SPEA2 on the set of multi-objective optimization problem under simulation. So, we will see the simulations now. We will take the first problem set as a ZDT problems. These problems says that we will be minimizing the F1 objective and the F2 objective will be written in terms of g and the function h, which is again made of f1 and g. All the variables are lying between 0 to 1. So, the details of the ZDT problems can be found in the given paper. The parameters which we have set for ZDT problem, we have taken population size 100, we are going to run for 200 generation, crossover probability 0.9, mutation probability 1 by n, eta c 15, eta m 20, and since we have the archive in SPA2, so we are keeping the same archive size as the population. So, currently it is 100. Let us begin with the first problem, which is known as ZDT1 problem. Here the F1 objective is x1 and the F2 objective, which is made of the function g and h, are given here. This is a 30 variable problem, and since it is a mathematical problem, so we know where is the Pareto optimal front, and it is a convex Pareto front. We can see this is the initial population and the red line represents the Pareto front for the given problem. So, the solutions are distributed and they are far from the front, and after 200 generation we can see the solutions are well converged and there is a diversity as well among the solutions that are converged on the Pareto front. Let us look into the simulation now. Here we can see these solutions are moving towards the front, and when they are close we can see the solutions have distributed nicely over the Pareto front, which is shown in the red line. Now we will go to the another problem, which is called ZDT2 problem. In this case, we can see that the form of G has been the same, but the H is different, and because of this H, the F2 and F1 nature is going to be different, and for the given problem we are going to get the non-convex Pareto optimal front. This problem is also a 30 variable problem. So, as we can see, the initial population is started a little far from the Pareto front, and after running the algorithm for 200 generation, the solutions are converged. So, we can see that SPA2 can very well solve the problem which has non-convex Pareto optimal front. Let us see the simulation for the same problem. So, here we can see the solutions are kind of at the two corners, but when the solutions are moving towards the front, they are nicely distributed, and slowly they are moving towards the Pareto optimal front, which is shown in the red line. Moving to the third class of a problem, which is ZDT3. Here again the form of F1, F2 and G are the same, but H has been changed, and in this case, since the sin x function is included, so we can expect some disconnected Pareto optimal front for the given problem. This problem is also solved for 30 variable problem, and here the solutions are distributed. As you can see, the range of F2 is from 6.5 to 2. After 200 generation, the solutions are distributed on the disconnected front, and the range of F2 we can see from 1 to minus 0.8, and F1 is lying between 0 to 0.9. If we see how these solutions are moving towards the Pareto front, now we can see at the beginning itself these solutions are distributed in the disconnected front, and slowly they are moving towards the Pareto front, and at the bottom we can see we are going to get all the 5 disconnected front for the given problem. After ZDT3 we have ZDT4 problem. In the ZDT4 problem we can see the form of G is changed and H is the same as ZDT1, In this case, we will be solving a problem with a 10 variable here, except for x1, meaning that x1 will be lying between 0 to 1, and rest of the solutions will be lying between -5 to 5. The problem which we are going to solve has a convex Pareto-optimal front, and there will be lot of local Pareto-optimal solution, such as 21 to the power 9 or about 8 into 10 to the power 11 local Pareto-optimal solutions. The initial population for ZDT1 can be seen that it is started in F2 around 250 to 100, and F1 is in the range of 0 to 1 always. And after running this particular algorithm for many generations, so we can see that the solutions are well converged to the Pareto front. So we can see how SPA2 is performing on the given problem. As we can see, the solutions are moved to the one of the corner, and as soon as these solutions are moving towards the Pareto front, so these solutions get distributed along the front, and slowly these solutions will be converged on the Pareto front. For the given problem, since it is complex, we have run SPA2 for 300 generations to get the Pareto, to get the solutions converged on the Pareto optimal front. The last problem which we will be solving in ZDT problems, that is called ZDT6. Now in the ZDT6, the form of F1 has been changed. Similarly, we can see there is a change in G function as well as the H function. Since H is similar to ZDT2, the Pareto optimal front will be non-convex. We are going to solve this particular problem for 10 number of variables. So as we can see, the range of F2, the initial population is generated close to 8, 9, and F1 value between 0 from 0.2 to 1, and most of the solutions are generated on the one side of the objective space. And after running this SPA2 for many generations, as we can see that the solutions are converged on the Pareto front. If we see the simulation of SPA2 for the given problem, so we can see that the solutions are actually converged on the corner of this objective space. As soon as these solutions are converging towards the front, we can see that there is a good diversity, and since the problem is difficult, so we are running for more number of generation, and we can see slowly these solutions have converged on the Pareto front. So in this case, we have run SPA2 for 400 generation to get the solution on the Pareto optimal front. After the class of ZDT problems, as we have understood that these ZDT problems are two objective problems, and some problems are easy to solve, some problems are non-convex, some problem have a lot of local Pareto optimum solutions, and so on. But these ZDT problems are always two objective problem. So the another class of problem on which we will see the performance of SPA2 is the DTLZ problem. These DTLZ problems are the scalable problem, meaning that we can solve for any number of objective function. So let us look into the DTLZ problem now. So these problems are proposed by the four authors, and from their surname the name came out as a DTLZ problem. The parameters which we have chosen to check the performance of SPA2, the population size is 300, generation is 500, crossover probability we kept it 1, probability of mutation is 1 by n, eta c 30, eta m 20, and here also we are keeping the archive size same as the population size, which is 300. Let us see the DTLZ1 first. Since the problem is scalable, so we can see that how we can write objective from F1 to Fm. So, capital M represents the number of objective. In this DTLZ1, all the variables are lying between 0 to 1. If we look into the form, we have g function which is written in the various objective function. So, here we can see the g function is written which has xi 0.5 whole square and some cost term. For solving DTLZ1 problem, we have taken a parameter k which is the cardinality of xm equals to 5. So, the number of variable for DTLZ problem will become m plus k minus 1. M is the number of objective, k is 5 and minus 1. Now, here the Pareto optimal front for DTLZ1 is a plane, and the difficulty or the characteristic of a DTLZ1 problem is it has 11 to the power k minus 1 local Pareto optimal fronts. We can see the simulation now. So, first we will see the initial population. Now, we can see the range of F1, F2 and F3. So, these solutions are starting very far from the Pareto optimal surface. Since it is a 3 objective problem, so we call it as a Pareto optimal surface. And after running for 500 generation, we can see on the right hand side figure that all these solutions are converged to the Pareto surface, as well as we have a good diversity among the solution. So, we will see the simulation of SPEA2 for DTLZ1. So, we can see that the solutions are converging towards the front, which are quite far and close to 140 generation. Some solutions are converged and the rest of the solutions thereafter converged on the Pareto surface. Now, here the solutions are keep on changing their position. It is only because we have the truncation method or operator to keep the diverse solution on the Pareto surface. The next class of problem is DTLZ2. Here the form of DTLZ2 is different from DTLZ1. It involves cos and sine functions. Similarly, we have this xi, the all variables will be lying between 0 to 1, and the g function as given here. For solving DTLZ2 problem, we have taken k equals to 10. The number of variable will be m plus k minus 1, meaning that if we take 3 number of objective, so 3 plus 10 minus 1 means the number of variable will become 12. Here the Pareto optimal front will be Fm square for all the objectives, and in this case this is going to be the quarter of the sphere. We can see the initial population is generated, which is quite far, and after running SPEA2, the solutions are converged on the Pareto surface, which we can see on the right hand side, and they are also diverse. We will see the simulation for the given problem. So, we can see within 30 generations the solutions are converged to the Pareto front, and they keep on changing their position because the truncation method is selecting the solutions, or we can say the truncation method deleting those solutions which are crowded. Since we have run SPEA2 for 500, we can see that the solutions are converged on the Pareto front. Another class of problem is called DTLZ3. The form of F1, F2, Fm again have been changed. Still it has cos and sine functions, and the g function which is used with these F1, F2 till Fm, the form has also been changed. In this case, while solving DTLZ3 problem, we are taking k equals to 10, number of variable is equals to m plus k minus 1, which is the same as in our previous problems, and if we look at the Pareto front, it is going to be the same as DTLZ3. However, this particular problem is going to have many local Pareto-optimal fronts. This is the initial population which we can see on the left hand side. If we look at the F1, F2 and F3 values, we can see that these solutions are very far from the Pareto surface. And after running this SPA2 algorithm for 500 generation, the solutions have well converged on the Pareto surface, and there is enough diversity to represent the surface. Let us see the simulation now. We can see these solutions are keep on improving and moving towards the Pareto surface, and after few generations these solutions will be trying to converge on the Pareto surface. So, close to 360 generations, these solutions are now converged, and we can see that not only convergence, there is a good diversity among the solutions which are converged on the Pareto surface. Come to the last problem which we have taken in this particular session. This is DTLZ4. In this DTLZ4 problem, we can see the form of F1, F2, Fm that have been changed now. Although these are cos and sine function, but inside it the xi to the power alpha. So, the alpha has been introduced here, and the variables are going to be lying between 0 to 1, and GM form is also changed. For solving this DTLZ4 problem, we have taken k equals to 10, number of variable as the same, which is m plus k minus 1, alpha has been taken 100. The Pareto optimal front for the given problem is the same as DTLZ2, and we are going to see how SPA2 is going to perform. The initial population, as we can see, it is generated on the one side of the objective space, and after running this algorithm for 500 generation, we can see that the solutions are converged on the Pareto surface. We will see the simulation now. Now, we can see the quickly within 50 generation, these solutions are converged to the Pareto surface. So, initially this solution started from the one of the corners of the objective space, but as soon as the solution converges to the front, the solution get distributed on the Pareto optimal surface. So, from in this session which we have dedicated to SPA2, we have come to the closure of this session. In this particular session, we started understanding the SPA2 on our generalized framework. On this framework, since SPA2 uses different kind of ranking as well as a diversity, we understood SPA2 through a working example. So, in this session, we discussed about the fine grain fitness through strength and raw fitness. We also did hand calculation for kth nearest neighbor approach for diversity. We also discussed about the archive truncation method, and we discussed the survival stage. The SPA2, the original version, incorporates the SBX crossover operator and mutation operator for generating the offspring population, as well as the binary tournament selection was used, that is with replacement. In order to see the performance of SPA2, we tested on the two test problems, which are ZDT problem set and the DTLZ problem set. From the simulations, we can see that when the problem has the non-convex front, convex front, disconnected front, or there are many local Pareto optimal solutions or front, in those different situations, SPA2 was able to converge in all of the solutions, and there was a good diversity among the solution. So, with this understanding on SPA2, I conclude the session on this algorithm, which is called SPA2. Thank you very much.